Okay, chapter 3.
Yes. Can you?
Hopefully I have it. Okay.
Yeah, this one. So 4a.
4a.
So I know that it's like you're moving x to y, and then you're multiplying x by y, and then you're adding 5, but it just I couldn't figure out what was the right one. What was the input they were looking for? Yeah.
Oh, it doesn't work?
Well, I put like x equal x.
Did you put the return in?
Yep, that was my thing. We were working on it together.
Okay, so you did return. So because in RAX that's the return value, so you need to return, and then what are you returning? It looks like you move x into RAX, and then you multiply y to it, and then you add 5. So return x times y, and then plus 5. And then with the semicolon. Did you put the semicolon in?
Yeah, we tried that.
Yeah, okay. So it didn't work for me.
We literally tried that.
You tried exactly that.
Mm-hmm.
I mean, so
maybe I missed the semicolon.
there are bugs in this. So yeah, but if you
this isn't for a grade, but that's what
this is not for a grade, but we would appreciate bug reports. Like if you if you find them. Yeah. So this is the very first iteration. In fact, this is actually not even a week old. What's it? Oh, the same as your Meta CTF logins. I made them exactly the same. Your Odin ID, your Odin ID is the username, and the last 4 digits of your PSU ID is the password. So yeah, I think I'll just keep on doing whatever chapter or whatever problem you want done.
The other one, it was, at least for me, I was going down.
Okay.
Where not this one. Yeah, actually this one. It's a problem from the book, but if we could go over a little bit to explain how we find the size of the array, like
the size of the dimension of the column.
Yes,
Okay.
like if you just theoretically. I know that I could figure it out from the book. It's exactly like the book, but I couldn't figure it out myself to have understanding of it.
Let me.
And even with the CTFs, I couldn't.
Really?
Yeah. Just there.
Well, I was hoping to put it right next to here, but really? If the screen is at the bottom, turn adjustment a quarter turn.
That's like Meta CTF. Now you have to figure it out.
Forget it. There, I'll use Notepad.
screen cast.
All right. All right. So here is Notepad, and I'll put it right next to it. So here, this is RDX. RDX gets 8 times RDI plus RDI.
So it's 8.
So that's 9.
Oh.
And RDI is I.
Why it's 9? So it's 0.
It's 8 RDI plus RDI, which is 8x or 8I plus I.
Okay.
How far down?
This is chapter 3, problem 7. I'll put that right there. So this is RDX is now 9I, and this is RDX is equal to 9I plus RSI, which is J. This one says 4 RSI plus RSI, and put that into RAX. So this is RAX is equal to 5J. This one says take RDI and set that equal to 5J, and RDI had I in it, but now RDI now has 5J plus I. That's what that one does. Source destination. Now these are the 2 money instructions. This is you take whatever is at Q plus 8 times RDI. So what's in RDI is 5j plus I. And you know that that is going to be Q of ji. Right? So you remember that formula for the two-dimensional matrices? If you are in the jth row, so you want to get to the jth row. How do you get to the jth row? It's the number of columns times j times the size of your data type. Your size of your data type is 8
Yes.
bytes. These are longs. So it's the size of your data type times number of columns times j. So this is your number of columns in Q, which is 5.
Now you're creating how many columns?
Yeah. So this is, so let me do this. This is equal to Q plus, dereferencing Q plus 8 times 5 times j plus 8 times I. Right? And so the 8 times I will get you, after you got to that row, will get you to the right column in that row. And then this is the number of columns here. The Q, or the P, sorry, the next one does, this is P plus 8 times RDX. Well, RDX has 9I plus J, right? And so this is P plus 8 times 9 times I plus 8 times j is P of I, j. So now, in order to get to the ith row of P, I need to take the size of the data type, 8, times the number of columns in P, times the row that I'm looking for. So then the number of columns in P is 9. So this matrix, so then number of columns in P, which is basically n in this declaration, is 9. And this one, the number of columns is 5. Yeah.
Does that mean that the money operation is actually the stuff that's like the first load-in for both of those objects? So the LEA quads are both the... Yeah. Because those are the ones where you're actually loading the first, like, integer into it.
Sure, if you look at it that way. Yeah. This is where you generate the 9, and this is where you generate the 5. Yeah, that's true.
So we both, I mean, in general, when you have the quad, you have the first one, so you're incrementing the first RSI plus 4 times RSI. So that's how it becomes 5.
But it's important. Actually, I would always write it out this way because it might not be a number that is going to show up like this.
Okay.
This is good because, 9 is right next to 8,
Okay.
and then 5 is right next to 4. So that's why you get that. But you should actually write it all out and then see what is actually being done here to get your indices.
So a typical, like, before final question. Let's say you kind of have figured it out and you write down with your own words, but you have some mistake instead of 4. I don't know. You don't have the computation exactly correct. You can get some.
If you write it all out,
yes,
yes. So that's important. Yeah, if I can actually decode what you're thinking, I can give you partial credit. That is correct. Yeah. In fact, if you do this, and I see a mistake somewhere there, I'm more likely than not going to take much off at all.
You're like, oh, thank you.
Right? So yeah, if I see this scrawled on the side, that really helps me give credit on a problem. But if you just print n is equal to 2 and m is equal to 8, yeah, nothing.
So we're better off core dumping our brain.
Well, okay, I also, the percentage of stuff that you get incorrect in your write-up is weighed against the percentage of stuff you get correct. So there is that.
It's a balance.
Yeah. Yeah. All right. Another one.
Then you just have to
Let me do some chapter 8 ones because we haven't really. It seems like we didn't do a lot of chapter 8 in terms of practice problems. So let's do the bottom two. What is the output of this program first? And I'll let you guys work on it. Actually, yeah. So, I didn't bring any scrap paper. Anyone have scrap paper they can... Oh wait, I do have a couple sheets.
Here, I got it.
Yeah, I have 3 sheets of scrap paper here.
Here's some.
No, we got it. We got this.
You got? Oh, as people need it.
Like, white paper.
All right, cool.
I like to pick that.
do it by itself. It's not moving. Huh?
Oh, all right. So the child hits A and then hits B, and then the parent will finally, this weight will succeed, and then the parent will hit B. So this is ABB.
So to
Yay.
show our work on that one, to get as many points as possible for us people.
I would do the horizontal forking thing. Yeah, if you draw me that figure and it's mostly correct, I give you most of the credit. Yeah, that's what I would do on that one. And then this one, what did you guys get? Uh,
32.
32, I think. But
That's 10 limit.
2 to the 5th.
yeah, so after the 0th iteration, it's 2. After the first iteration, it's 4, etc. And then after the 4th iteration, it's going to be 32.
So why doesn't each child process actually process like another 4? And
So
You're on lesson 5 is 5 times.
5 times through, and then it's
So
basically
it's
doubling each time.
yeah, but it's gonna like once you do the first
Let me
one,
see.
right? Then you're gonna
Oh,
have
yeah, good
one
job.
child who's gonna process.
After this first fork, now you have 2 children going through this exact loop in the I equal 1 iteration. And then you'll have that fork, and now you'll have 4 children. And then 4 children, all forking, will give you 8 children. And then 2 more times. And then you get this 32 times. Alright. So the next thing I want to do, let me see here. I actually want to give you even more practice on this, so I am going to go to the practice problem. Let me see if I can mute this so as not to give you the... Oh wait, yeah. Never mind. Give you some other ones. Let's do this one. This is the last problem in the practice set.
Yeah, that's what I was saying.
Oh, this came up
Yeah,
while
it
I was doing the other. Oh, that's what you were talking about. Huh.
Yeah, it was going out.
And now it's stuck.
Yeah.
All right. Well, I'll do that now. Actually, it's better if I write it on here. Well,
It's like life. You try hard for something.
this is the last problem in that final review PDF. So there's lots of questions in this final review, and the solutions are provided. Yeah, try and work through them without the solutions first, which is what we're doing here. Because I didn't really give you a lot of practice doing this in class. So
Well, we just learned about it today.
yeah, you just learned about it today, and yeah. So this installs two handlers, one on alarm and one on child. So both the parent and the child have these two handlers installed. So that's the first thing. Then you do the fork, and here you have the child, and the child immediately pauses. So the child can't print anything out right now. And then the parent is here, and the parent sends the child PID a SIG alarm. And then the parent pauses. Okay, so now the action goes back to the child. And the child gets this SIG alarm. And remember, we installed a handler. Both the child and the parent have this SIG alarm handler, and this is the handler right up here. So we established on the SIG alarm signal, we establish handler alarm on the child when it gets that alarm. So nothing gets printed out so far. As soon as you get the child running the handler up here, you print D. And then you exit 0. So the first one is D. The first thing you print out is D.
And the child gets killed.
And then the child exits. So, and moreover, it exits with the status code of 0. So when the child exits, it's going to do what for the parent?
Signal.
Send a SIG child to the parent. Right? I terminated. You better do something about me. And because the parent was here paused, it's going to get that SIG child signal, and it's going to come up here and handle it. And it's going to say, hey, what was the child's status? I'll wait on that. And then I will print E:% %D, where %D is the exit status of that child, which happened to be 0. And then the parent is going to exit. So it will never hit C. It will never hit the rest of this code, B or C. So then the next thing is E:0. And that's it. That's it.
Oh, the exit. I didn't see the exit.
Yeah, you see the exit here. Yeah, on there. So.
The exit closes the process entirely.
Yep. Doesn't ever get back here. It just exits out of that signal handler. You're done.
Not just the function. It's not just like a normal break.
It is a break, sort of. It's almost like a function call, but you have the exit right at the end. When you call exit, yeah. Exit never returns.
It's like a super break.
Yeah. Exit never returns. Done. Let's do the one above it.
And that exit function is installed. It's just the compiler puts it in the code for exit.
Yeah, when you return out of main, it eventually will call exit. Yeah. Or you can explicitly call it if you'd like. Yeah.
Can you overload the exit function?
You can overload the libc exits call, just like you could overload the random number. You guys did the random number one? Yeah, you could overload that one too. So, yes. So this is another one of these. Actually, I'll put it in PowerPoint because
You can put it inside the song.
PowerPoint in Microsoft has everything in the kitchen sink.
I
in it.
only ever use it.
all right. And then what I can do is write on it. Okay, so let's start here. We'll say C, which is counter, is 5. And then I'm going to fork. And the child is up top. So the first thing this does is decrement the counter. So now C is equal to 4. And then the parent is going to increment the counter. So now C is equal to 6 down here. And then it's going to pause. The child does another fork. And then its child will decrement the counter again. So this is C is equal to 3. And then it's actually going to printf 3. And then this middle guy is going to pause. So then this is 3 gets printed out is the first thing. This child is now going to fall through to the end and then exit. And then when it exits, it's going to signal this person right here. So this was paused. And because I installed this signal handler in the parent, that means everybody's got that signal handler. So this signal handler will get called on this process, which is this middle one here.
How do you want to show signal handling like that?
You could put a dotted line here that says, I am done. I will signal. That's not much of a dotted line. So you could say, this guy finishes, this process finishes, sends a sig child. At this point, this pause is going to get that signal. It's going to do a wait on the child, and then it will print its own value of counter. Now, its own value of counter is 4. So then 4 gets printed. And then this child exits. So then this child is going to now exit, and this parent, the original parent, which was paused, will now get a sig child, and it will also call the handler child. And at this point, it prints out its value of the counter, and its value of the counter was 6. So 3, 4, 6.
So in the diagram, the first time it goes down, it prints 3, then goes down.
And then the counter
4
was 4 here, and the counter was 6 here.
Okay.
This is why, like, if you draw that, if you draw something like this, then I know you understand most of the problem. And then, yeah, then the mistakes will be a minor deduction. This will, whenever it returns like this without the explicit exit, it'll eventually call exit. Yeah.
Exit 0, right?
Yeah. It will. Yeah. If you do a return 0, yeah.
Non-explicit exit is exit 0. Is that technically a signal that's sent to the process that actually, like is a non-exited main technically a signal?
Yeah, it will sig child, and it'll be a normal exit. Yeah, those are normal exits.
Well, because the parent of the program, isn't that a child of like something else, like the shell?
It is.
So then it's gonna have to sig child to the shell.
Eventually, it'll go up the. Okay.
What number was that? 6, 7, or 8. I don't know. It doesn't really matter if we're just drawing it out, really.
Yeah, it was the last. So the last 2 signal problems in the practice, the final review, are what we just did. So I think that's pretty good.
Battleship with caches.
We could do cache. Well, now I'll do requests because I think that was.
We do a cache problem or 2.
All right, do a cache problem. Which one do you want to do? Actually, I want to do let's see here. Let's do number 5 first. Because I definitely want you guys to know your sizing of caches and what can be stored in it. So yeah, I'll do this one. All right, so how big is this cache? Number of sets times the number of lines per set. In this case, it's just 1 because it's direct math. Number of sets, number of lines per set, which is 1, so 256, times number of bytes per line. So this is 256 times 16, which is
It's just 256.
4096.
4096. Let me submit. Oh no, it crashed. Oh, there we go. Good job. Yeah, it's ready to crash. I'll kick it. All right, how many short data types fit into this cache?
Divided by
2048. So the short data type is 2 bytes.
So 2 bytes.
So 2 bytes. So divide that by 2.
Thank you so much for posting this, because I would not have thought about asking about.
What would be the hit rate for sequential access of this data type through this cache? So this forces you to look at the block size. So the block size is going to determine the hit rate on sequential access. So you remember when there was only one sort of element in that line, then you would always miss. But when you increase the line size, or the block size, then you get spatial locality. So the first one will miss, and then the subsequent ones will hit. So in this case, your block size is 16. Is it almost time to go?
So 15 are going to hit.
But what is your data type? It's a short, it's 2 bytes. So remember, this is sequential access of this data type, which is the short. So the first short is going to miss. How many more shorts are you going to have in that line that will hit? 7. So yeah, 87.5%. So miss and then 7 hits. So this is 7 divided by 8, which is 87.5.
Oh, that's what you're looking for.
Okay, can you submit 7 divided by 8? I want to see how it compares.
No. Well, if you wanted to support that, maybe you can help. Yeah,
On the actual
submit a pull request. Patch it.
On the actual exam, is it okay if
Why
we do
wouldn't
7
I
and
support
8,
that?
other than the percentage? I can't.
Oh, yeah. This is just for the web. The website is because she's trying to metamorph it. Also, you'll get a different problem than what this is. So yeah.
No, I totally understand.
yeah.
That makes sense. I was just
One of the things that you might get asked is if you doubled the line size, what does it do to the hit rate? Or miss rate even. It would have the miss rate. So that's what you have to know.
doubling the line size, half the miss rate.
The miss rate, yeah.
The miss rate.
The miss rate. So the miss rate here was 12.5. If you doubled the line size, it would go down to 6.25.
Cut the line size in half,
Double the miss rate, yep. Okay, now we can do one of these cache lookup ones. Now I'm going to have to reduce it to get this all on the same. All right, we'll do that. We'll do this one. Are my clocks not right? Everyone's waiting outside.
No, it's 34.
Okay.
We're good. We still have tons of time.
I'm so sorry to interrupt, but I think I left an exam sitting on
Oh.
in the previous class, and before it gets distributed, I just thought
Yeah,
I'd double
come
check.
take a look.
I'm so sorry.
No problem.
I don't see it. I'm so sorry to interrupt you guys. No, it's not an evaluation, it's an exam. Pardon? No, that's fine. Sorry, thank you.
So does everyone sort of know how to attack this problem? You have to figure out which bits are being used for the byte offset, which bits are used for the set index, and then the rest is the tag. So your access is hex 634. So you blow that up into bits, and then you organize the bits. You classify which bits are for each. So how many bits are in the block offset? there are 4 bytes in a block, so there would be 2 bits to determine which one of these bytes you want. So the least significant 2 bits are the block offset. How many bits are for the set?
You have.
We have 8 sets, 0 through
So-
7. How many bits do you need to index 8 things? 3 bits. Log base 2 of 8. So this is 3 zeros, 001, 010, all the way to 111. So last 2 bits are the byte offset. The next 3 bits are the set index. The rest is the tag.
The next, wait, you said 2, 3, and then the rest are the time.
Yeah.
I just want to make sure.
0, 0,
And
1, 1.
what's the?
So then now you can reorganize these bits to figure out what is the set, what is the tag, and do I hit in this cache?
That means the tag is actually really big, right? Because the tag is the other, like, 7 bits. 8. Bits inside the data array, right?
Yeah, the tag will be a larger number of bits. And I will also do a PowerPoint thing on this too. Straighten that. Okay, so for this one, so we'll write out the address as 000, 0110 is the 6, 0011 is the 3, 0100 is the 4. This is your block offset. This is your set index. This is your tag. Your tag is hex 31 because this is where you put the boundary. Okay, so your set is hex 5, and your block offset is hex 0. So you go into set 5. You see that your tag matches 31. You are looking for byte number 0, and in this case, up here I've labeled going from 0 to 3. So that's the byte AB. So this is a hit.
Wait, why is the tag 031?
Because when you reorganize the bits, you take these 4 bits to be 1, and then the next 4 bits to be 3. Because you're using the low 5 bits for the block offset and the set index, and so that's why it's not, it's not in a nice nibble boundary. So that's why you have to reorganize the bits out of this hex address.
So in order to get as many points out of this as possible, you suggest that we write the hex for each one of those?
The first thing I would do is write this all out.
Yeah.
And then show me which parts are for the bits, which part is for the set, and which part is the tag.
Yeah.
And then to write each one of these. And then after you've figured out the tag, the set, and the byte offset, you can just go directly to the set, look at the tag, and then, give me the byte offset. So let's, and of course, do this again in your practice because you'll get something different. So let me go back to the website. block offset was 0. Slow.
Oh.
No, it's wrong. Not happy. 0, x 0. Oh yeah. All right. Set index is 5. Job. Cache tag was hex 31. This is a hit.
How we did determine if it was hit or miss?
Because when you look into the cache at set 5, set 5 had a tag that was 31, and there was data associated with it, so that's a hit. If you matched the tag but there was no data in there, that means it was invalid. So I think that's what I write.
Yeah.
Right above.
You
Cache lines that are empty or invalid.
Right. That's what we would write.
Miss. If there was no data there, then that's considered a miss.
Byte offset is the bytes in the actual.
What value is returned if it's a hit? So we saw here that the offset was 0, so we're going to return AB. All right. So then we're all good. We're green.
Why did it say B again? I'm sorry.
Because it was byte 0.
Okay.
So byte 0 is AB, byte 1 is 9-1. So I labeled this 0 to 3. So I'll try and keep the same labeling on an exam. Well, hopefully if I remember the ordering. Yeah.
What happens if we access, if we cache an address and then go to read an address that has everything is the same that we have in truncate out of 10? As far as like, is it going to create a collision?
No collisions because we're using the rest of the address bits to uniquely identify the data that's in that cache line. So there's no collision there because then you actually belong in that cache line if you match the tag. There's no other thing that can not belong in that line.
Aren't we like in this example, weren't we trimming off the first 3?
The first 5 is just identifying which set you're in, and then the offset within the matched block. Those are, because everything else is unique, you can guarantee that one is saying which part of the cache do I look at, and then the other part is saying this is my exact tag, and that's the only address that could have that tag in that set with that range of offsets. Yeah.
But I mean, with our address, you have like 3 or 4 bits at the beginning of the address that you weren't using. Right?
So I didn't write it down, but yeah, there should be a leading 0 in front. But those just because I don't write them down, those bits are already there, the zeros. So you couldn't put an address that had a 1 in those most significant bits, and then I would have to change my address. So the tag is unique. In this case, there was 5. Actually, there's only 8 bits in the tag because there's 13 bits in the address, and 5 of them are used for the set and the block. So yeah, there's only ever 2 nibbles at the top. So I've written out the tag in its entirety. Okay. What else do you want? Should we do Chapter 5?
How much assembly is going to be on the final? Like, other than like what we had before in Chapter 3, where we were decoding the array, is that like the extent of our assembly? Or are we going to have to be doing like some more of the CTF stuff? Like, where in memory is this being stored? What frame is this in? Or anything like
CTF stuff? No.
What instructions are you going to want us to know?
Moves and LEA quads and adds,
What about
that kind of stuff.
flags? Are we going to have to...
You will need to know conditional jump, like
Right.
some of those.
Like the SF and the-
No. Yeah, I skimmed over that pretty good. So
So
no.
you want us to know like jump is equal or jump
Jump equal, jump
Jump
less
not
than,
equal.
jump less than or equal, what
jump
those
not
mean.
equal.
Yeah.
Okay. So you want us to understand.
And I think if you guys are, there are some problems here.
Yeah, there's a bunch of jump.
There's a couple with conditionals in here, I think. Or not.
There's at least one with the J.
Oh, that
Yeah,
was
this
switch
one.
statement.
Except I already solved it. Right. I should have deleted my database.
Oh, you can walk us through it.
Yeah, so in this case this is a for loop and it's missing the actual, so here you don't really have to decode the jump less than, but you see for I is 0, I less than 31, and you can see the I less than 31 right here, because you're comparing the index to 31, and if it's less than 31, then you go to L3, and then you do an add, and then you add 1 to the index. So in this loop, you can decode that I is stored in RDX, and that this is the loop check at the bottom. And then in the inside, this is taking your result and adding RDI to it, which is A. Well, actually, first of all, I have to figure out A gets added to B right at the top. So they're zeroed out here, and then in RDI, you add B to it. So A plus B. Now RDI has A plus B. A plus B gets added to the result in this loop. So that's why this is result is equal to result.
Does that string have to match to get the answer?
It does.
There's a lot of ways you could express
But you see, this is, yeah, oh, I think she said that she tried to check for commutativity. So,
it. It's like a different operator, like
Actually,
result
it works.
plus equals B plus A.
not sure yet, because as soon as you answer it, you can't go and try a different answer to see, yeah, so.
That'd be okay.
But on an exam, if you give me result plus equal A plus B, I'm going to say yes. Yeah, I'm a better parser than Python is. Yeah.
Thank you.
Ooh, it's Python.
Yeah, it's in Python, yeah, if you guys. No, it's Flask. Python
What it
Flask.
should do is actually do an evaluation.
In some of her stuff, it does an evaluation, but that's highly dangerous. So, yeah, if you take my web security class, you'll see how highly dangerous that is. Yes. That would be a great thing to implement, yeah.
That'll be a great thing to implement.
A reset on this database to regenerate more, and then to morph it again to give you new problems. Yeah, reset and morph again would be an awesome feature to add. Yeah,
Per problem basis.
yeah, on a per problem basis. Yeah, that would be great. Actually, yeah, if you guys want a capstone project and want to build more stuff like this, try other courses in your undergraduate discipline to build stuff like this. Yeah, this would be awesome. Yeah, or yeah, a beta project. Hey, beta project. You get money to do this kind of stuff. They're accepting applications for the beta project in spring. They give you money to do a project of your choice. So I think it's like $1,000, and then all you have to work on something. Or there's an undergraduate research program that's also part of it. So yeah, if you are interested in doing and working on this kind of stuff, yeah, I'll help you out. Cash Battleship. Wait, who suggested that? You said it? Yeah, that would work. We are done. 3:49, and I have another walkthrough, screencast walkthrough from last quarter. I'll put that up there too, and then yeah, just keep on practicing. You guys do all right.